I'm Taryn Noble. I'm the project lead for marine sediments and sediment coring. So we're here to take sediment cores from around the Denman and Shackleton continental shelf, and also some deeper sediment cores. And the idea is that we can use these sediments to reconstruct how the ice sheet behaved in the past, and also looking at how biological productivity and carbon flux to the seafloor has changed. At the moment, we don't have a very good understanding about how the Denman Glacier responds to changes in climate. And so you can use marine sediments to go back in time. They use sound waves to penetrate into the sediment. That makes a map of the vertical structure of the sediments and how they're piling up and what the seafloor looks like. First, we have to do this survey work to find the best site. And we've got a 4-meter long square barrel, and that barrel has a big heavy weight attached to the top of it. And they put the system together and they raise it up off the A-frame, and then they lower it gently to about 30 meters above the seafloor. So you sort of wait for that to settle, and then you lower the core into the sediment. And so you don't just drop it, you sort of lower it at a particular wire speed. And then the idea is that the top of the weight is pushing down through layers of sediment that takes you further back in time.
Yeah, we're at 720 meters.
Copy that.
And then when you bring the core up, it's got what's called a core catcher at the bottom. And so it's got like a little trap door that comes down to stop the sediment from all falling out the bottom. It's a bit nerve-wracking and exciting. You bring the core back up and you're like, oh, did it work? Did we get something, or did we hit a rock? Because there's lots of icebergs around here that can drop big boulders. So once the core is back up, then we bring it into the lab, and then the coring techs help us take the lid off, and then we can survey the treasure that we've picked up from the seafloor. Right now, I just brought up the castle core, and we have taken the lid off, and the first thing we have to do is sample for ancient DNA, and so that's why we have to dress up in our masks and gloves so that we don't contaminate the sample. The chock-a-block full of mud. It's really fantastic fill catch. With ancient DNA techniques, what you can do is extract the DNA that's sitting around the clays, and these are just fragments of all the different types of algae and zooplankton and all the different bugs in the ocean. And we can look at bacteria, like the biologists go nuts on this, right? Because you can have so much data.
It's exactly what I hoped for, and it's really exciting.
We have these sort of layer cake structure in the core that's related to different types of sediment. The different layers can tell us about different processes that are happening either on the ice sheet or in the ocean. What we're finding in the sediment cores is that we have these thick layers of diatom mats. There's a particular species of diatom. It's an algae that grows its skeleton out of glass. They make these beautiful glass houses, and so when they sink to the sea floor during the summer, they grow like really prolifically, and at a certain point they die out and they sink, and they preserve in the sediment for hundreds of thousands of years. And so they can be sort of key species that tell us about extinction events. So if we want to date sediment cores, that's often quite challenging, but we can use the disappearance or occurrence of particular key species of these diatom shells that we see in the sediment to say, okay, we know that has to be at least 50,000 years old or 200,000 years old. So they're very useful both for environmental reconstructions of what the surface ocean conditions were like, but also as markers for time. We have some nice sediment cores that are deeper, about 2,000 meters below the surface of the ocean. And these cores are interesting because they can go back much further back in time than what we see close to Antarctica, because they haven't been affected by erosion of the ice sheet. And so these records accumulate much more sediment. So in our 4-meter long core barrel, we might have 200,000 years of sediment as opposed to a few thousand years when we're close to the shelf. Out there, it's really totally different environment. We've got icebergs coming from all around Antarctica. We've got different types of fossils. We've got carbonate shells that fall to the seafloor and not many diatoms. And so there we can look at how ocean currents have changed through time and how we can have a much longer signal of how the Denman Glacier has varied through time because we get a more continuous, older package of sediment. I think it's really important to have archives that go further back in time because the work that we're doing here is really important, but it's just a snapshot in the year 2025 about what the conditions were like. And what we can do with the sediment archives that we get is provide a sort of richer understanding of the temporal scales. We're all trying to understand the climate processes that are governing ice sheet change, but we're doing it from different perspectives and on different timescales.